Welcome back to the class on electrical mechanics. In this lecture, we are going to discuss about the rotating magnetic field. How we are going to create a rotating magnetic field in a three-phase induction motor. That we are going to see now. To create a rotating magnetic field, it requires a three-phase winding is displaced by 140 degrees in space. In that winding, I have to send the three-phase current so that the rotating field will be created. See here we are saying that 140 degrees in space. Suppose if you are assuming that the stator winding is designed for the two pole, then the mechanical degree is equal to the electrical degrees. Here we have taken the stator. This is the A phase, A dash. This is B, B dash. This is C, C dash. A is nothing but a starting point of the coil. Here A dash is nothing but a finishing terminal of a coil. The same manner, B is nothing but a starting terminal of the coil. B dash is nothing but a finishing terminal of the coil. C is nothing but a starting terminal of the C coil. C dash is nothing but a finishing terminal of the C coil. The three windings, those three windings may connect in a star or delta depending upon the requirement. So finally, we are getting the three terminals outside. For these three terminals, if we apply the three-phase supply, then the rotating field will be creating from this stator winding. Now here, what is the condition here? 120 degrees in a space. Suppose if you take this is the axis of the A phase. Now this is the B phase. The angle between the A phase and B phase is the 120 degrees. Again, the angle between the B phase and C phase is the 120 degrees. So in that manner, we kept the stator winding in a stator so that it will be creating a rotating magnetic field. Now that we are going to see graphically. This is the A phase. This is starting terminal. This cross is representing the current entering into the coil. This dot is representing the current leaving from the coil. Now apply the right hand thumb rule. Close the four fingers in the direction of the current which is going into the coil. This thumb is representing the flux which is creating from the coil, that is phi A. This phi A is nothing but this is the axis of the flux which is creating from the A coil. Now the B coil is here. Again you close the four fingers in the direction of how the current is going into the coil. Now the current is going in this manner. Now this thumb is representing the direction of the flux that we are showing here. These are the positive direction of the flux coming from the B coil. The same manner, this is the C coil. Now the current is entering in this direction. So the thumb is representing the direction of the flux which is coming from the C coil. So that we are representing here phi C. Three fluxes which are creating from the phase A, phase B, phase C. In a space, the angle between the fluxes also the 120 degrees. So one more important point here is that all these fluxes are the sinusoidal fluxes. These are the axis only. In this axis, suppose if you take this is phi A. In this axis, the flux magnitude will be changes. The direction also will be changes a regular interval of time. The same thing is happening for the phi B and phi C also. So whatever the direction we have shown here, those are nothing but a positive directions of the flux creating from the coil A, coil B, and coil C. Now these are the sinusoidal fluxes because we apply the sinusoidal voltage to the stator winding. The sinusoidal current is passing through the stator winding. So the flux creating from the stator winding also the sinusoidal. Now these are represented here mathematically phi A equal to phi m sin omega t. This is the flux creating from the coil 1. Phi B equal to phi m sin omega t minus 120. This is the flux creating from the second coil. Phi C equal to pi m sin omega t minus 240 degrees. This is the flux creating from the C coil. Here pi m is nothing but a maximum value of per phase flux. The same thing we are going to represent graphically also. This is the phase A flux. This is phase B flux. This is also sinusoidal. But the angle between the phase A and phase B is the 120 degrees. This is the phase C flux. The angle between the phase B and phase C is the 120 degrees. Now we are going to find out what is the resultant flux which is experiencing in the stator. That we are going to find out by taking the different intervals. Again, we have taken the same expression for the flux coming from the each phase, pi A, pi B, pi C. Here we frame a one table, omega t equal to 0 degrees, 60 degrees, 120 degrees, 180 degrees, 240 degrees, 300 degrees, and 360 degrees. Nothing but we are going to consider the one cycle. So in place of omega t, you substitute the 0 degree here, the magnitude of the pi A we are finding, that value are taken here. The same manner, suppose if you want to find out the pi b, in place of omega t, you take the 0 degree, find the value of pi b, that is minus 0.866 pi m. Similarly, take the omega t equal to 0 in this expression and find the magnitude of the flux coming from the C phase, that we are getting the 0.866 pi. Same manner, you repeat the same thing for the 60 degrees. Suppose in place of omega t, if you take 60 degrees, you are getting a 0.866 pi m. This is the flux coming from the phase A. This is the flux coming from the phase B. This is the flux coming from the phase C. Nothing but in this place, you take the omega t equal to 60 degrees. Then you are getting the 0. The same calculation you have to repeat for the every degree, 120 degrees, 180 degrees, 240 degrees, 300 degrees, 360 degrees. In your hand, you have how much these flux is coming from each phase. Now we are going to find out the resultant flux in a space. So here, if you observe this value, one phase is giving a positive flux, another phase is giving a negative flux. So here we have taken the reference flux. Already we have taken theta. This is the reference direction for the pi A. This is the reference direction for the pi B. This is the reference direction for the pi C flux. Nothing but now at 0 degree, now we are going to find out what is the position and magnitude of the resultant flux. The flux coming from the pi A becomes 0. Otherwise, this vector becomes a 0. The flux coming from the pi B becomes a minus 0.866 pi m. Otherwise, opposite to this one. Here you have to take it because it is minus. The flux coming from the C phase is 0.866 pi m. So this is the position. We draw here. This is the minus pi b. This is minus pi c. If you find the resultant of these two vectors, you will get in the pi r. That is the this is the axis of the resultant flux. Now we are going to find out how much is the magnitude of it. We know the resultant of the two vectors, square root of a square plus b square, just 2 into ab cos theta. When theta is nothing but an angle between these two vectors. So whenever we reverse this vector, this angle becomes a 60 degrees. Now the magnitude of A becomes a, see here, this vector magnitude becomes a 0.866 pi m. The magnitude of second vector becomes a 0.866 pi m. 2 into, again, magnitude of first vector and magnitude of second vector, the cos of the angle between the two vectors. If you simplify this one, finally you are getting the 1.5 pi m. This is the direction of the resultant flux. The magnitude of this resultant flux becomes a 1.5 pi m, where pi m is nothing but a maximum value of flux coming from the one phase. The same manner, we are going to find out what is the resultant flux at a 60 degrees. At a 60 degrees, the magnitude of the pi a becomes 0.866 pi a, nothing but this is the same direction. But the flux coming from the B becomes a negative flux. So we have to make it reverse this one, pi b here this side. Now you find the resultant of these two phases. It will give the resultant vector. The flux coming from the C phase becomes a 0. The same thing we are showing here. This is pi a, this is minus pi b, this is resultant vector. The magnitude of these two vectors are equal. Again, the angle between these two is 60 degrees. So if you apply the Pythagoras theorem to find the magnitude of this one, again you are getting the same magnitude, that is the 1.5 pi. Next, you repeat the same thing at 120 degrees. At 120 degrees, the flux coming from the pi a becomes a 0.866 pi a. The flux coming from the pi b becomes a 0. The flux coming from the pi c becomes a C phase becomes a minus 0.866 pi m. So this flux becomes a 0. This is pi a. Reverse this one. So we are getting the vector here minus pi c. Now you find the resultant of this two. The same thing we are showing here. Third diagram. This is the resultant vector. Magnitude of this resultant vector is the same, that is 1.5 pi m, because the angle between these two vectors becomes 60 degrees. Magnitudes are also equal. Now we are going to find out at 180 degrees. At 180 degrees, the flux coming from the phase A becomes a 0. Flux coming from the phase B becomes a positive, whereas the flux coming from phase C becomes a negative. So we have to make it reverse this one. This vector becomes a 0. We have only this vector in reverse of this vector. Find the resultant of these two vectors that we have shown here. This is the resultant. Again, the magnitude of the resultant flux is 1.5 times the pi. In this manner, we are going to calculate at 240. At 240 degrees, the pi a becomes a minus 0.866 pi m. Pi b becomes a 0.866 pi m. Pi c becomes a 0. So this value becomes a 0. We have to make it reverse this one. And we have to find out the resultant of these two phasors that we have shown here. This is pi r. Again, the magnitude of the resultant flux is same. That is 1.5 times the pi r. At 300 degrees, you repeat the same calculation. Pi a becomes a minus 0.866 pi m. The flux coming from the phase B becomes a 0. The flux coming from the phase C becomes a 0.866 pi m. So we have to make it reverse the pi a flux to find the resultant of these two. Because this value becomes a 0 that we have shown here, we are getting the resultant flux. At 360 degrees, the flux coming from the phase A becomes a 0. Phase C becomes a minus 0.866 pi m. The flux coming from the phase C becomes a 0.866 pi m. So you have to make it phase B becomes a reverse. You are getting this side. This value becomes a 0. Now you have to find out the resultant of this. This is the resultant flux whose magnitude is same, that is equal to 1.5 times the pi m. So from this case to this case, if you observe the resultant vector, this is the axis of the resultant vector. After 60 degrees, the resultant vector also will be displaced by 60 degrees. At 120 degrees, the resultant vector also will be displaced by 120 degrees in space when compared to the first one. Here again displaced by 60 degrees, again displaced by 60 degrees, again displaced by 60 degrees, again displaced by 60 degrees. So finally it comes to the initial position. Nothing but the axis of the flux within the stator will be rotating, whose magnitude is equal to the 1.5 times the pi. We have discussed about the how the rotating flux will be created from the stator winding or synchronous speed. Synchronous, the meaning of the synchronous is constant speed. So whatever the flux coming from the stator winding, that is a constant, 1.5 times the pi m. Moreover, how much speed it is rotating, it is also the constant. So that speed we are calling as a synchronous speed. The speed at which the stator flux is rotating is nothing but a synchronous speed. It is a constant, ns equal to 120 f by t. Next, one more important point here, what you have to remember is the magnitude of the rotating flux is 1.5 times the pi m. These are the 2 points what you have to remember regarding to the rotating magnetic field. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of my YouTube channel so that I'm always available to answer all your